Everything's good.
All right. Well, thank you very much. My name is Luke Beckwith. I'm a PhD student at George Mason University, as well as a part-time engineer at PQCrypto. And this is Robert Wallace, who's a master's level student at GMU. And we're presenting our research on a high-performance implementation of the LESS digital signature scheme. So first, we'll start with a quick snapshot of the current landscape of PQC digital signatures and the competition. We'll then have a very brief overview of the background of LESS, the algorithms, and the level of explanation an implementer can give on the math. And then we'll go over hardware architecture, particularly the module that performs Gaussian elimination before comparing with the results of other signature schemes. So first, as I'm sure you're aware, there have already been 3 algorithms for digital signatures selected for standardization. We have Dilithium and Falcon as the lattice-based schemes and Sphinx Plus as a symmetric scheme. And then this past month, 40 additional signature algorithms were announced. So plenty of work for us implementers to do. And this work focuses on LESS, which is one of the code-based algorithms. So LESS stands for the linear equivalence signature scheme, which is based on the linear equivalence problem, which is used to construct an identification protocol and then convert it to a signature using Fiat-Shamir. So the main functional elements that you're working with are large matrices with elements modulo a medium-sized prime Q. And then the core operation is this multiplication of a generator times a monomial and conversion back to the reducer echelon form. So first, a brief summary of those core concepts for the algorithm. So reducer echelon form is a form that a matrix can be in, and is said to be in if it meets the following 4 criteria. So any non-zero rows are at the bottom of the matrix. The leftmost entry, the leading entry, is to the right of all the entries above it, so it forms a staircase pattern. Those leading entries must be scaled to 1, and then all other entries in the leading columns must be 0. So those leading entries are called pivots, and the columns containing them pivot columns. Then to the 2 types of matrices involved. So first, a monomial matrix is just a combination of a scalar and permutation matrix. So it has exactly 1 non-zero entry in each row and column. And the effect that it has during multiplication is just permuting and scaling of the columns. And then you, of course, have the generator matrix, which is just a matrix whose columns form the linear basis of some code. So for a generator G of a code C, you obtain the code word by M times G. So then 2 generators are said to be linear equivalent if there is an invertible matrix S and a monomial Q such that you can convert one to the other. So if you have G prime and G, there's an S and Q such that G prime equals SGQ. And the portion that's relevant for, or the hard problem that's relevant for this is that if you just have G prime and G, it's difficult to recover the monomial Q. So then this is used to construct an identification protocol as follows. So the monomial serves as a secret key, and it's combined with a public generator G to form the public key G prime. The commitment is then generated by sampling another random monomial, combining it with the public data, and hashing it as the commitment. The response to the 1-bit challenge for the 0 challenge is just the monomial Q tilde, and for the 1 challenge is the secret monomial times the random monomial that was used in the commit. So in the case of the challenge bit is 0, the result is trivial because it's just G times Q tilde, which is what the commit was, and the response for the challenge bit 1 is G times Q inverse times Q tilde, which also holds true. And then for the syntax that's used for the number of key pairs, the first key pair is considered to be kind of the trivial key pair, the identity matrix in G, and the second key pair is Q and G prime. So then for the actual algorithms of LESS and key generation, first S-1 additional key pairs are calculated by sampling S-1 random monomials, multiplying it by the public matrix G0, and then the result is serves as the public key. And during this operation, all of the others, the most expensive algorithmic step is the conversion to reducer echelon form, so that'll be highlighted on each slide. Signing is again defined using Fiat-Shamir. So first, T commitments are calculated all at once using the same approach of a random monomial times G. All of the commitments are then hashed along with a message to form the seed D, which is then expanded into a challenge containing T entries, omega of which are non-zero. And then all responses are calculated at once. And again, the non-zero responses are where the secret key is involved in the signature. So then during verification, The challenge is resampled. All T responses are multiplied by the corresponding public key, and they are hashed to see if the seed D matches the seed they received. So one thing to note is that both signing and verification require T of these RF operations, so the performance of signing and verification are approximately the same. So then touching on the parameters used in LESS, first are the code parameters, which define the size of the matrices and the sizes of the elements in them. So for security level 1, you have already 252 by 126 matrices, and then getting up to security level 5, you have 550 by 274 matrices with 127 serving as the modulus. So these are very large matrices with a moderate-sized prime for the modulus. And then within each security level, they have these 3 different parameter sets, optimizing for either minimum signature size, minimum combined public key and signature size, or intermediate, which is a balance in between. So then touching on the code parameters. So T, again, is the number of times that you iterate the Sigma protocol. So for the lowest security level, that's down at 250, and at the highest, it's up at almost 1,400. So we have a very large amount of those multiplications and RF operations being performed in both sign and verification. And then again, omega is the number of non-zero responses, and S is the number of key pairs that are used. So roughly, in LESS with these parameters, as the size of KT and omega increases, the signature size increases, so as you perform more iterations of the protocol. For the public key, it's dependent only on the dimensions of the matrices and the number of keys that are included. And then the seeker key is independent of size, since it's always sampled from one 32-byte seed. And then in our architecture, the area is proportional to the number of columns n, and the keygen latency is proported to k and s, and sign latency to k and t. So the architecture for this can be roughly grouped into 5 sections of submodules that do operations on their respective objects, so those doing monomial operations, those doing generator operations. As you can see from that bold text and green arrow, the RF operation consumes the vast majority of the resources and the latency. So we'll focus on that for the remainder of our talk, which will be covered by Robert.
Hi. So for the RF operation, we're converting a regular matrix into the row-reduced echelon form. So basically, the goal here is to find our pivots for each row and to convert them to a 1 and zeros above and below it. So all of the arithmetic operations are going to be performed modulo Q, and then in an example that I'm going to show, that Q will be equal to 7, so it's easier to follow. So to start this, we first need to find our first pivot, so we can reduce each row of the matrix. So to find the first pivot for row 0, you start at the leftmost column, and then you scan down the column until you find the first non-zero element. Once you find that first non-zero element, which is a 2 in this case, you then want to swap it so that pivot row, which is here that we found, is in the same row as the row to reduce. In this case, it's the same spot, so it swaps in place. And then we want to change that pivot element, which is a 2, so it is a 1. So we multiply that entire pivot row by the inverse of the pivot element. And then so now we have a 1 for the pivot. And then next step, we need to make it so all of the other rows have a 0. So that way there's zeros in that pivot column above and below the pivot. And so to do so, we look at this original row, in this case the 3315 row. We look at the element in the pivot column, we multiply that element by the rescaled pivot row, and then we subtract that result here from the original row, and then that gives us this new reduced row. And then we repeat that step for the other row, and then we have zeros below the pivot. And then what we can do at the same time as while we're doing that is we can also search for the next pivot for the next row to reduce. Since we know that row to reduce is 1, we can search in this blue highlighted area where we scan down the leftmost column in that area until we find the first non-zero element. So there's a 0 there first, and then we find the 5 is our next pivot element. So because 5 is our next pivot element, we need to swap it back so it's in the correct row to reduce. So we perform that swap here. And then we want to then rescale that pivot element so it is a 1. So you repeat that step that we described earlier. You multiply that entire pivot row by the inverse of the pivot element. that rescales the pivot row. And then we want to reduce all of the other rows so that there is a 0 above and below the pivot element. And then while we're doing that next step, we also, again, search for the next pivot in this smaller search area, which happens to be this 4, because we keep scanning down the row until we find it. So once we found the 4, we can then repeat. We do a swap in place. We rescale the pivot row with the inverse of the pivot element. And then we reduce all of the other rows. And then that results into our row-reduced echelon form of the matrix. So what we can see from this is that there are 4 major operations performed in every iteration of the algorithm. We do a pivot search, we do a row swap, we do a rescale of the pivot row, and then we reduce all of the other rows. And all 4 of those operations are performed k times. You need to do all 4 of those for each row in the matrix. And then steps 3 and 4 require iterating over the entire matrix, so that's another k steps. So the general complexity of the algorithm is k squared. But there are some opportunities that we can take for parallelization to optimize this algorithm. One thing that we noticed is that when we perform arithmetic, it's typically one scalar multiplied by an entire row or element-wise subtraction between 2 rows. And then another thing that we noticed is that we can perform the pivot search at the same time as the reduce other rows. That way we don't have to search and then do things and then search again and then do things. And then we also found that you can, the reduce other rows step, all of the reduction is independent of each other. So you can do them in any order that you need, or you can do multiple of them at the same time. And then of course we have a necessity for a constant time implementation. So to describe the scheduling of how we achieve those optimizations. So first, while we're loading the matrix into the internal memory of the RF module, we can perform our first pivot search. Because each row is going to get loaded in, so we might as well search for the pivot while we're there. And since we need a constant time search, we technically need to scan the entire search area, even though most of the time you'll probably find it in the first column. Then we can perform our row swap, which we'll have to always spend 1 cycle doing the swap. And then we can perform our rescale pivot row. Since we're rescaling the entire row at one time in parallel, we can spend 1 cycle doing that. And then we need to spend the k cycles to reduce all of the other rows. And then, of course, because we're doing that reduce other rows and we have those results already, we can search at the same time as reducing the other rows. And so the latency of our implementation can be described by this equation here. It's k squared plus 3k plus 58. So the k squared comes from the inherent latency of the algorithm where you have to iterate over k rows k times. The 3k comes from the pipeline stages. There's 3 cycles of downtime between rescaling the pivot row and reducing the other rows. And then the 58 comes from filling up a pipeline. And I'll describe that soon. So first, how do we store the matrix? Well, internally, we want to have access to an entire row of the matrix at one time. So we have n separate RAMs so that we have each for 1 column of the matrix. And then by having it in 1 column in each RAM, you can access an entire row at 1 cycle. So that gives us a parallel memory access. We use this blue highlighted address translation RAMs, so we can do a row swap with 1 cycle by simply just swapping where the translation table is pointing to. And then we have a separate input and output ports here, so we can perform pipeline operations. So for the arithmetic, we have access to an entire row from the memory, so we want to be able to perform the multiplication between 1 scalar element and the entire row. So we have n parallel multipliers here. And then we also have n parallel subtraction, so we can do the element-wise subtraction. But we can also take advantage of the fact that the reduce scale row occurs before the reduce other row step. So we can reuse the hardware here because we have to do the reduce scale row first. And then we can also observe that this critical path is it's long, but it basically waterfalls down. So we can very easily pipeline this to take advantage and increase our clock frequency. And then we also have registers here to hold the reduce pivot row so it can be used during the reduce other row step. So quick example of how we can use it to rescale the pivot row. You have our row here, which is our pivot row. We can extract our pivot element here, find the inverse using that lookup table, and then multiply it by the entire row. And then that can get written into these registers so we can use it later and also get written back into the memory. And then when we do the reduce other row step, you have to iterate over the rest of the rows. But for one example, we have the entire row here. We can extract that pivot element there, multiply it by the reduced pivot row, the rescaled pivot row, which is in these registers here. We multiply it, and then we can subtract it from the original row, and then that allows us to reuse this hardware for 2 separate operations. So we can pipeline this as well to make it a higher clock frequency. We insert these pipeline registers in red. It's really just a design choice on where you place them or how many you want to place. But right now the critical path is in this N1 multiplexer, and that gives us these frequency results here. So at the lower values of N, we can get up to 200 megahertz, and then it goes down as you increase N. And then, yeah, so to cover the overall results of the RF operation. So because we have N parallel units operating on a row, the area is directly proportional to N. And then because of that N-to-1 multiplexer, as N increases, our frequency will decrease. And then, of course, our latency is predominantly k-squared. And then, of course, the area significantly increases as you go. And you can see that the BRAM utilization for because we have to hold the entire matrix, it gets pretty large, up to 56.5. And the latency, of course, is very high in the clock cycles.
All right, so that brings us to the results for the algorithm as a whole. So first, we'll start by comparing with the software implementation. So this is comparing our work signified by this work with the optimized AVX2 implementation running on a Ryzen 5 CPU, whereas our hardware is running on a relatively inexpensive RTX 7 FPGA. So the clock frequency is limited by the clock frequency of RF. So the CPU is running at 3.9 gigahertz. Our hardware is only running at 142 megahertz. So there's an order of difference by a factor of 27 between the clock frequencies, but even with that difference in frequencies, we're still able to improve key generation by a factor of 1.4 and signing by a factor of 2.5. So then before touching on the comparison with the other hardware implementations for Sphinx, Falcon, and Dilithium, just as a bit of context, here is the comparison of the transmission costs for the public key and signatures. So you can see, obviously, the lattices are doing the best between these 4 algorithms. And then comparing Sphinx to LESS, LESS does achieve slightly smaller signatures for the short parameter set, but at the cost of much larger public keys. And that's because you have the very large generator matrices that you need to transmit. And for the short parameters, you have multiple of those matrices. But then moving on to the hardware comparison. So mostly focusing on the comparison with Sphinx Plus, even the signature latency is about an order of magnitude slower than Sphinx Plus. And then verification for Sphinx Plus is actually fairly fast compared to signing. So LESS verification is several orders of magnitude slower than Sphinx verification. Comparing the area results, LESS requires about twice as many lookup tables, which are the core logical elements, roughly the same number of DSPs and flip-flops, where DSPs are for multiplication and flip-flops are for storage. And then 6 times more block RAM, again, because during RF, you have to store those very large matrices. So in conclusion, this work has presented the first work on this algorithm LESS, which is based on a new hard problem linear equivalence problem. Our implementation is able to improve over the software implementation by a factor of about 2 times. And then comparing to Sphinx Plus, while the signature sizes are slightly smaller, that does come at the cost of larger public keys and slower signing and verification. So that concludes our talk. If there are any questions, we'll welcome them.
Okay. Can you comment on the side channel resistance? You mentioned that it was constant time, but there are other, for example, are you and have any defenses against DPH style attacks?
So this implementation doesn't have any power side channel analysis protection. It only has the constant time. So resistant against timing attacks, but no countermeasures for power attacks.
Thank you.
I don't see any other questions, so I think we can thank the speakers again.